All right, so we're going to discuss how we can solve circuits that have BJTs in them. At this point, we're going to concern ourselves with the DC response, which is, large signal when we talk about this type of circuits in this course. So it's going to be the large signal analysis of BJT circuits. We talked about NPN devices the introduced NPN devices in the previous lecture, and today we follow with that, and then I'll talk to you about what the difference between an NPN device and a PNP device is. So here is an NPN device, a reminder of what we talked about. IC goes in, IE comes out, and IB goes in. I have three terminals and label the voltages accordingly. So I have VCE between the collector and emitter, VBE between the emitter and base and emitter actually, and then VBC between base and collector. So when I say VBE, I mean VB minus VE, right? And this is the device, and we said that we go and use this model for the device to analyze circuits that contain a BJT in them. So you take the BJT out, you replace it with this model. We said there are two, but this is the preferred one in terms of models. This IC is ISE to the VBE over VT and beta IB. If the device is in active region, this is VBE, this is IB, IE, and IC. So for device in active region, this is what we have. And then what did active mean? Well, we said there are three regions that we usually use these devices on. In, active, cutoff, and saturation. And there was a reverse active that we tried to avoid. It should not happen normally. And then depending on the operating region of the base emitter and base collector diodes, for active region, BE is on, BC is off. We need that current source between base and collector, or between collector and emitter. In cutoff, both of them were off. And in saturation, both of them are on. Right? So these are the three operating regions. I suggest that you go and read the textbook, check the slides, make sure that you understand the difference between these regions. And we said that, normally at the beginning at least, what we do is that we draw these little diodes here to remind ourselves of the directions and how we wanted the voltages and currents to be. So this is the discussion from the last lecture. Now we want to actually start using this device. So this lecture is mainly about solving a couple of examples. So here is an example. It says if VBE on is 0.7 volts and beta is 50, solve the circuit. Solving the circuit means that you calculate all voltages and currents in that circuit. We calculate all the main ones, and the other ones can basically follow, right? And here's the circuit. Now, notice that in this case, I actually don't know the operating region of the transistor. It could be any of those three. So these labels for the currents are for myself so that I remember what is what. And this is my two little diodes. Okay? And then obviously this is going to be my VC, this is my VE, and VB is here, which is, in this case, ground. So VB, VC, VE are labels, not sources. Okay, so let me see what I can do about this circuit. The first thing I notice is that I can write a bunch of KVLs and KCLs here. So, for example, I can write a KVL in this loop. You can start from 0, the base, or let me just use the labels here. So VB is equal to VBE plus, let me call this bottom supply VEE, the top supply VCC. VBE plus IE times RE plus VE. Okay, so that's the KVL that I have in the bottom loop. The top loop, I can write a KVL over there as well. So VCC is equal to ICRC, the voltage drop across the resistor, plus VC, that's it. Or VCB if I want to end at ground, right? So VCB goes, so this voltage plus this voltage, and then I'm at the ground. Okay? So these are the two KVLs and KCLs, the KVLs that I have. And then I noticed that if I look at this circuit, I don't know VB, well, I know VBE because I'm going to assume that the device is on. I don't know IE, IC, or VCB. None of these I know. VB I know is 0. So the easy one is that VB is 0. So let me not do that. It's just going to add to okay, because the base is grounded. But I have 3 variables in here on the 2 equations. So I need at least one more equation to solve this circuit. I go and use one of the equations that I have for the device. I can say that IC I know is beta IB or alpha IE. I don't have anything that tells me IB, so this is the equation that I use. I say I know IC is alpha IE. Okay? Now, 3 equations, 3 unknowns, I should be able to solve the circuit. This one here, so let's call this the star equation. That one I actually can solve independently. It looks like I have enough voltage to turn BE on. I'm going to assume the device is in active region. From that equation, the first one I have over here, I can see that VBE is assumed to be 0.7 volts when the diode is on. So I can see that 0.7 plus IERE minus 10 is 0. And from here I can see that IE is in fact 9.3 divided by 10 kilo ohm, and that's 0.93 milliamps. Okay, so I determined IE. Then from this third equation here, I can figure out IC. For a beta of 50, alpha is going to be 50 over 51. Go back to the previous lecture if you need to know why, times 0.93. And that is going to be essentially the same, but if you want to be super accurate, it's going to be 0.91 milliamps. Okay? So I have IC and IE, and then I can plug it into the second equation here and figure out my VC. That's the only thing I don't know. VCB, in this case, B is 0, so it's just VC. So from the second equation then, I see that 10 for VCC is equal to IC, I already know, 0.91 milliamps times RC, which is 5 kilo ohms, plus VC. And here gives me a VC of 5.45 volts. If I want to find IB, I can use the other equation, IC over beta, and see that IB is 18.2 micrams. So I have all the voltages and currents. If you, for example, want to find VE, VE is going to be VB minus VBE. VB is 0, and therefore VB I know is 0.7, it's going to be minus 0.7 volts. So that's all the voltages and currents I have in this circuit. I have solved the circuit. Am I done? Well, no, because I made the assumption here when I was using this equation, right? When I use that expression that relates IC and IE through alpha, I assume the device is in active region. If in fact my assumption is not right, well, I've used the wrong assumption to solve the circuit, and therefore my solution will not be correct. So what I need to do is that I need to verify my assumption. So go back, check VBE. Can it be 0.7 volts? Yes, in that circuit it can be. You know, you can accommodate 0.7 volts on that diode, so that is okay. BE on, you know, like the diode circuits that we've done before. But I need to check BC. So I calculate the BC diode. VBC is 0 minus the collector voltage I have here, 5.45 volts. So this is minus 5.45. So this is VBC across this diode here. A voltage, the voltage is negative, so this is less than 0, so this is BC off. So this is the conclusion. This was for BE, this was for BC, so therefore active. Okay. I solved the circuit with the assumption of active region. I verified my assumption. In this case, in this manner, when you think about these circuits, it's actually like, you know, when you go back to your diode circuits that we learned in the previous chapter, it's like solving a circuit with two diodes, right? So remember that what we did is that we assumed an operating region, hopefully an educated guess that would get us to the correct answer in the minimum number of steps. But at the end of the story, we always had to go back and verify the assumption. Same thing here, a BJT is like two diodes. Once you make an assumption, you have to go back and verify it at the end of the work. All right, so we learned how to analyze NPN circuits, at least under active conditions for now. I'm going to jump to the PNP structure, PNP device, and talk about that, solve that, and then go back and, or introduce that and then go back and maybe look at the device behavior in other operating regions. A PNP device is made the opposite way of an NPN. In an NPN you have N region at the top, N region at the bottom, and a P in between. In a PNP you have the opposite. We have the same names for the three terminals, but we put it upside down. This is the symbol for a PNP device because of the way it is made. The emitter we usually put at the top. It has to be at the higher potential compared to base to make the base emitter diode on. Remember, the active region or all those operating region definitions were based on whether the diodes are on or off. Well, now you have two diodes that are facing this way. Remember, for the NPN, the diodes were facing from base to the collector or base to the emitter. For a PNP, it's going to be the opposite, right? So you have one diode here, one diode here. And that's really the main difference. That's all there is to it. That usually, because of the way the diodes are facing, the emitter, base, and collector are biased differently. In most circuit drawings, we have more positive voltages at the top of the page, more negative voltages at the bottom of the page. And if that is the convention, usually the emitter is connected to a higher voltage close to the top of the page and the collector for PNP towards the bottom of the page, and then we flip the device and show it this way. Now, one difference between the two transistors is the direction of currents. For an NPN, the directions are the opposite. So IE goes in while IC and IB come out of those terminals. And again, that's because of how we use this. A PNP is closer to the power supply, the positive supply, and therefore the current from the collector usually goes into something else at the bottom, and this convention makes my life a bit easier. If you want to go and use the circuit model that we had, especially for the active region, this is the one that we use for a PNP. So again, this is your emitter, IE, IC, and IB. So base, emitter, and collector. And for a device in active region, I need to emphasize that this IC follows the same equation. IC is IS e to the VEB in this case, because remember the diode, in order for it to be on, V emitter has to be larger than V base, but the other equation is the same, I beta IB, and this is your VEB. Again, VEB means VE minus V base. That has to be positive for the base emitter diode to be forward biased. Okay, so that's all there is to it. The difference between a PNP and NPN device is that simple. The equations, again, I'm going to write them here. So IC is beta IB and alpha IE with the convention for the currents as shown over there. And there's also this exponential relationship between IS and IC. The only point to remember is that it is VEB for PNP. And if you are super accurate, add that one over there too. Okay? Very similar. Equations are the same, just keep in mind the direction of the currents and orientation of the diodes, and basically you're dealing with a device that is in terms of how we treat it is similar to a BJT, NPN BJT. So here is an example with a PNP. I have a new circuit here and I want to solve it. So this is the circuit. Slightly different from the one that we just saw. So in this case, the base is not connected to ground. You have a resistor between the base and ground. I'm going to label the currents here. And again, stick to the convention. We do not choose the directions of the currents here. We stick to the convention, making our lives easier for the analysis of these circuits. So RB in this case is 100 kilo ohms. RC is 5 kilo ohms. RE is 5 kilo ohms. VCC here is plus 10 volts, and VEE down here is minus 10 volts. Okay? So the question is, solve the circuit. What are the assumptions? VEB on, when the diode is on, is 0.7 volts. Assume VB, we measured it, is 1 volt. And when we are solving the circuit, what are VC, VE, IC, IE, IB, and in this case we also want to know beta, right? Because we do not know it, we use the transistor, made the circuit, built that configuration and measured VB. We notice it's 100 kilo ohms, and now we need to solve the circuit. All right, so KVLs and KCLs that I can write. So this is one KVL, this is one loop, and again, you by now should be a little bit more comfortable when I call that a loop, because remember, there's a voltage source here that has one end connected to ground, one end over there, and you actually have a loop. But I draw that and I call it a loop. That loop, I can write my KVL. It tells VCC is equal to IE times RE, the voltage drop across that resistor, plus VEB, the emitter base voltage, plus VB. And VB in this case, I can write that equation based on IBRB. Or I know this is VB. Okay? And that's it. I actually can figure out what IB is from this equation here. I already know VB is IBRB. And I can also write a KVL here for this loop. I don't like that KVL, because again, remember that I'm going across a current source between base and collector, or between collector and emitter, either one. At the collector terminal, you have a current source, and you write a KVL around the current source, you have two unknowns. Well, in this case, you don't know IC because we still haven't figured out IB and IE, but also you don't know the voltage drop across the current source. It's like writing this KCL at a node where you have a voltage source attached to it. The current from the voltage source can be anything. So if you don't know the voltage at that node, you add two unknowns to the system of equations. So KVL, when you go across a current source, is not really that helpful. You still need to figure out other equations to basically be able to solve that system. Now, so I let that be for now, and then I'll try to see if I can figure out enough material from here based on these two equations. I know that if I assume active, I get another equation that says IC is beta IB or alpha IE. And I need that equation as well because I need to figure out what beta is. Okay, so from this second equation down here, that's easy. I can calculate IB right away. IB is VB that I measured. It was an input to the problem. And that's 1 divided by 100K, and that's 10 microamp. Good. What does the first equation tell me? The first equation, I can, put in the values there. 10 is equal to IE, RE. RE is already known, 5 kilo ohms. Plus VEB, I'm assuming is 0.7 volts. The diode is on. I have 10 volts on one side of the diode, 0 on the other side. It can be on, so that's a good assumption. And IBRB or VB, that was 1. And from here, the only unknown is IE. I can right away calculate IE to be 1.66 milliamps. All right. So I have IE and IB, and one of the other equations that I have from KCL is IE is IC plus IB. So I can calculate IC. IC is going to be 1.66 milliamps minus 10 microamps, so it's going to be 0.01 milliamps, and that's 1.65 milliamps. Now I have IC, combining these two, then I can see that beta is the ratio of the two currents, IC to IB, and that's 165. So I solved that part. I'm still not too sure if my transistor is in active region. I need to come back and make sure that is the case, but if I just define beta to be the ratio of IC and IB, that looks to be the case. So the remaining task is to calculate VC. Well, I've already calculated IC, and I can write a KVL from this point downwards, right? I'm not going across the current source anymore. I just write VC as in terms of the voltages that are below it all the way to ground. So VC is RCIC plus VE, right? And that is going to be, I already know IC, 1.65 milliamps and 5 kiloohms, so it's 5 kiloohms times 1.65 milliamps minus 10, and that is going to be minus 1.75 volts. Okay, if this is true, I've solved the circuit. I know VE, VC, VB, and all the currents, right? So one last thing I need to do is check active. So I need to make sure that BE is on and BC is off. The active region, the definition is the same as NPN. So BE, can it be on or not? Yes, I have 10 volts at the top that has gone through this diode that I, again, say that you should draw on your first few problems. So I have 10 volts on the P side of that diode, something close to 0 on the N side, or actually I know exactly 1 volt on the N side. So VBE, VEB can be larger than 0, so this is okay. BC off, I calculate VBC. VBC, I know VC is minus 1.75. VBC is 1 volt on the base side minus 1.75 volt on the collector side. That's 2.75. Well, it is positive, but this is VBC, right? This is VBC. I actually should look at VCB if I want to talk about that diode specifically. So what I do is that, therefore, VCB, which is the voltage drop across the diode, is minus 2.75 volts, right? It's the negative of VBC, which is less than 0, and therefore BC is off. BE on, BC off, check. My assumption of active operating region was correct, and I can use the results that I have in the above. Okay, so solving NPN and PNP transistors are essentially the same. I just have to be mindful of the directions of the currents and voltages, basically the symbols. Now, what if the transistor is not in the active region, right? So if it is in cutoff, if you do the calculations and it turns out that the transistor is in cutoff region, both diodes are off, great, it's the easiest one to solve. You have two diodes that are off, the currents for all three terminals will be 0, and therefore your life is the easiest it can be. But what if it's not in active or cutoff, and reverse active, let's assume you've been smart enough to not do it in that region, not put your transistor in that region. We are all hopefully going to avoid that region. At least never put the device in that region, but intentionally. And then you are dealing with a device in saturation region. So in saturation, what happened is that for both NPN and PNP devices, the BE is on, BE diode is on, and BC diode is on as well. So let's look at an NPN device and see what happens in this case. So this is your NPN device, and PNP is going to be the same. And these are my little guys that make all the magic happen, the two diodes, right? Collector, emitter, base. And again, IB goes in, IC goes in, IE comes out for an NPN device. If that's the case, now remember that we said the doping on the N side for emitter is higher than the doping for the N side for the collector. So the structure of the device, if I again go and look at the semiconductor, I have N region here, P region here, N plus here. The doping on the N side at the emitter is higher. So let's say if the doping at the collector, I'm going to just use some numbers here. So this is 10 to the 16 atoms per cubic centimeter. This P region can be 10 to the 17 per cubic centimeter, and this is 10 to the 18 per cubic centimeter. So there is a significant difference between the amount of dopants on the emitter side than the collector side. And what that does is that, I have two diodes. They have two PN junctions, so I have this diode and this diode. But because of that significant difference in the doping of the N sides of these two diodes, they are a little bit different. And the main difference is that for a given current, or the main thing that happens, for a given current, let's say 1 milliamp for both, VBE on is going to be larger than VBC on. There's a ton of things that is going on, but the gist of it is that at the end of the story, for 1 milliamp, if you push 1 milliamp through the base emitter diode and 1 milliamp through the base collector diode when they're on, VBE on is slightly larger. How much larger? Typically by about 0.1 to 0.2 volts, right? So if VBC on is 0.6 volts, VBE on will be around 0.7, maybe 0.8 volts, right? Now, what is the implication or what is the end result when it happens? I'm going to make a larger drawing of that diode, so let me just go here. Okay. So the little guy that you know what? I'm going to use a slightly thicker line here as well, just in case things don't transpire well. Okay. So I have this diode that is on. Remember, we're talking about saturation region now, okay? And that diode that is on. If this diode is on, this VBE on appears here. So let's say I have a transistor where VBE on is equal to VBC on plus 0.2, right? This device, for whatever reason, for the same level of the current for both diodes, I have 0.2 volts more across VBE on for, or if you want to, let's say, let's look at it a bit differently. So I say VBE on is, let's say, 0.7 volts, and VBC on is 0.5 volts. Okay? If that is the case, and I put this device in active region, then I have plus and minus 0.5 volts here, plus and minus 0.7 volts here. Okay? If you go around this device and do your calculations, and you can make your life a bit easier by connecting this to ground, assuming this is ground, calculate VB. If this is 0, this is going to be 0.7 volts. If this is 0.7, you go here and this is 0.2 volts. Okay? I may have said it a bit too quickly, but convince yourself that if both of these diodes are on, this voltage here, VCE, is around 0.2 volts. It's the difference between the turn-on voltage of the two diodes. If it is 0.1, it's 0.1. If it is 0.2, it is 0.2. So when the device is in saturation region, once you convince yourself that the device is in saturation region, you can go and show that, VCE is about 0.1, 0.2 volts, okay? So what I can do now is that I can come up with a new circuit model for this device. I can say that, okay, I don't have my nice current source between the base and between the collector and emitter anymore. Remember, I had that for active region. Base, emitter, collector. This is my VBE on, but the value of this is your VCE saturation. So that number is usually given to you, or so this is VCE saturation, right? It's either given to you, or you can look at it up from a data sheet, or it's just the difference between the turn-on voltage of the base and emitter diodes. So instead of that transistor, if I notice that the device is in saturation region, I use this model, put it inside of my transistor in the circuit, and solve the circuit. And for a PNP device, it's going to be very similar. It's just the polarities of the two voltage sources you have here will be opposite. Notice that the directions of currents will stay the same. We stick to the same convention as what we had before for the active region. The directions of the currents is always the same. Now, let's look at one example. Okay, so it says solve the circuit. What do we know? We know that beta is 100 and VBE on is 0.7 volts and VCE sat is 0.2 volts. You don't know what the operating region of the transistor is at the very beginning, right? So because in vast majority of the cases the device will be biased to be in the active region, it is usually my starting assumption, and I solve the circuit with that assumption, and then go and fix my check my solution and make if in case I make mistakes or it doesn't hold up, I check other operating regions. And this is my VB. VC and VE is ground, and again I draw my little diodes here to remind myself of all those polarities and everything else that I need to keep in mind. Okay, so assuming active, I'm going to solve this circuit a bit quickly because we've gone through a similar situation before, and hopefully by now you have done a few yourselves as well. But assuming active, I can see that in this case I can write a KVL here. So VCC is equal to IB RB plus VBE. And from here I can right away figure out IB to be 10 minus 0.7 from here that I had, divided by RB. And RB is given in the experiment, in the problem, it's 100 kilo ohms here and 2 kilo ohms up here. So divided by 100 kilo ohms, and that's 9.3 micrograms. Because I know beta and I'm assuming active, then IC is going to be 100 times 9.3 micrograms, that's 930 micrograms or 0.93 milliamps. Okay? So I know my IB and IC, and therefore I can calculate VC. So I can do a KVL from VCC to this point and stop at VC. VC is VCC minus ICRC. That's 10 minus 2 kilo ohms times RC, IC of 0.93 milliamps. And that's 8.14 volts. Okay? And that's it. And then you're going to go and see if check active. I'm going to leave that to you to make sure that it is active. So it's just a quick example. I actually thought that this was going to be in saturation. It's not going to be. And let me turn it into a problem that is going to be in saturation. Same circuit. I'm going to change RC. Now, instead of 2 kilo ohms, I'm going to use 20 kilo ohms here. Let's say plus 10 up here, and then over here. Same circuit, right? Plus 10. And I do the same. If this is the case, I can still, calculate IB from the before, the same thing that I did in the above, and IB will be 9.3 microamps. If I assume active, IC will be 0.93 milliamps, same as above, and then I can calculate VC from, again, the thing that we did above, write a KVL from VCC to this point, this is VC, is going to be 10 minus 0.93 milliamps times 20 kilo ohms. And now if you do that, that's where the interesting stuff happens. This voltage will be minus 8.6 volts, which is a sign of problem because I cannot have a negative voltage here. Remember, at the end of the story, none of these devices is a generator. At DC, I cannot really have a negative voltage here. And this is a diode. This is a diode. I cannot produce a negative voltage without any switching or anything fancy in this circuit from a plus 10 volt supply. So if that's the case, this is an indicator of a problem. I cannot have a collector voltage that is less than the smallest voltage in my circuit. This indicates problem. As soon as that happens, the other thing I would notice is that my VB, if I go with the previous assumptions, is somewhere around 0.7 volts, right? So VB on was around 0.7 volts. So therefore VBC, the voltage drop across this diode, right, is going to be 0.7 minus 8.6. So that's 9.3 volts, which is actually much, much larger than the turn-on voltage of a diode. What that tells you is that BC cannot be off, which is the assumption for active region of operation. We assumed it, it turns out to be wrong. It cannot happen. So if BC is going to be on and BE seems to be on, happily on, the operating region that I should focus on is now saturation. So cannot be active. Remember, we assumed active, right? This whole calculation based on the previous KVLs assumed active, and then we figured that it cannot be active. The next one that is possible is saturation, because the diodes are actually on. It looks like the circuit is happy if the diodes are on, and that means that we cannot have cutoff. So the one that is remaining is saturation. I go and solve the circuit with the model for the transistor in saturation region. And that model is this. So I take the transistor out, put this equivalent circuit for it. So this is 0.2 volts, and let me just write the symbols. On the collector end, I have VCC, RC, and then this is IC. On the base end, I have RB and again VCC here. Okay? Actually, you can immediately see that this circuit is actually much, much easier to solve than the other one. I only have two branches, but they seem to be independent from each other. I actually can write a KVL here that is independent of this KVL here. There's really no connection between the two anymore. Makes my life easier. And therefore, I can quickly figure out that IB is going to be VCC minus VBE on divided by RB, which is what we have calculated before, 9.3 micrograms. But IC from the KVL on the right side is going to be 10 minus 0.2, the voltage drop across the collector, divided by the resistance in the collector, which was 20 kilo ohms. So that's 9.8. Sorry. 0.49 milliamps. And then IE obviously is the sum of the two. Which is going to be 0.499 milliamps. If you calculate the ratio of IC and IB, and this is a takeaway, and this is one indicator of saturation region, the ratio is going to be 0.49 divided by 9.3 is 52.7, which is less than the beta that was given to you for the active region of operation, right? So you calculate the ratio of collector and base current. You can sometimes do that in your circuits. And if that ratio is not beta, if it is less than what was given to you as the value for beta, that could be an indication of active saturation region. Otherwise, you just do your calculations and you see if the diodes are both on, and if they are both on, then that means the device is in active region. I'm going to kickstart one last example and show you how to solve it. I will let you finish the example. And here is our last example for the day. And then once you do this one, I strongly suggest you to go and look at the suggested problems. I hope that you've done a whole bunch of problems for diodes by this stage, and now go and practice a little bit of those suggested problems for BJTs. What we know for the devices, beta is 100, VBE on is 0.7, and VCE sat is 0.2. We don't know where the device is in terms of its active region, so we have all the information we need about the device so that we can solve the circuit in either case. This one is in your slides, so just in case something is not legible when I'm writing it here in the class, you can definitely go to your slides and have a look at the terms. So I'm going to kickstart the solution, but let you go through the actual calculations and okay. Okay, so those are my little diodes over there. So this task is to solve this circuit. You want to go and figure out all the voltages and currents here, and I'm going to write an equation for this node. I'm going to, well, it is the base node, the base of the transistor. Let's just call it VB. I can say that this current plus this current plus this current will add up to 0. So VB minus 0 divided by RB2 plus VB minus VCC divided by RB1, the current that goes up, plus IB is 0. I have two unknowns, IB and VB. Well, that's not very helpful. So I look for extra equations. So over here, I can write a KVL from VB to ground. I can go and say VB is equal to VBE plus IE times RE. Well, I introduced a new variable here, IE, but I'm not too scared of it because I already know IE is beta plus 1 times IB, right? So beta IB is IC, and IB, the sum of them will give you IE. So I'm not too scared of that. If I know beta and if I know IB from the previous equation, I can solve this. And then I go ahead and see if I can solve the circuit, and then once you have IB, so you get IB from these calculations, you go and calculate IC, then that lets you calculate VC. At the same time, you calculate IE, which lets you calculate VE, right? And from these two, from here and here, you can calculate VBC. From here and here, you can calculate VBE, and then verify if the device is in fact in active region. You assume active, so VB is assumed, so this one actually is assumed to be larger than VB, or your circuit let it to be on the order of VB on the turn-on voltage of a diode, but this one you have to check. You want to make sure that that diode is off. So that's one way of solving it, which is all good, and there's no problem with that. There is, however, an easier way of solving this circuit, and if you do that, instead of writing two equations to solve the circuit, you can do it with one shot. And that is by going and coming up with a Thevenin equivalent for this portion of the circuit. So remember, we can only have Thevenin and Norton equivalent circuits for linear circuits. Well, that portion of the circuit is definitely linear, right? You just have two resistors and a power supply at the top. So you take that part off from the whole circuit, you go and calculate the Thevenin equivalent circuit, which is one resistor here, one power supply here. You calculate those two based on the values that you have in your circuit, and then you attach them to the rest of the circuit. And everything based on the Thevenin theorem should stay as before. Your voltage and currents in the circuit should not be affected. So this should still be VB, this should still be VC as the previous one, and this should be RVE. Okay? Now why do I like this circuit? Because now I can write one KVL here and be done with it. How? If you write a KVL here, this is IB and this is IE. V Thevenin, assuming the device is in active region, V Thevenin is R Thevenin IB plus VBE plus IE RE, right? And again, I know that IE is